My name is Van, and I'll be sharing some things about some molding principles using vacuum in these next 30 minutes. Just some of the observations that I've made over the years and some of the experiences that I've had. And again, they're principles. As you look around this exhibition, there's some excellent examples of vacuum being used in presses, being used in molds, and it's being used all kinds of different ways. And there's some really good examples of what I'm going to be talking about on display with some of the equipment here. These are some of the principles behind it, why it works, how you can apply it, some things that some people don't really understand about using vacuum in a molding system. And so the idea of having a vacuum is that there's a lot of defects that can be minimized or eliminated by using vacuum. And this is fairly well documented over the many years. First time I ever had a chance to use a vacuum in a mold was probably almost 40 years ago. And then there were vacuum boxes that were put on some presses. Some of the companies in the U.S. were the first ones to actually have a vacuum chamber or vacuum box. And now they've started being pretty much used all over the world, and there's some excellent press manufacturers that are using the vacuum incorporated into the equipment. And so it's become very pervasive across the world. Rubber is well known to be an effective seal. That's what tires are doing. That's the reason that we have balloons or latex things. It's the reason we have bladders, because rubber holds and seals air. Okay, well, that's kind of good and it's kind of bad if you're trying to deal with a vacuum, because when rubber is going into a mold, it's pushing the air around. Air molecules slip past each other very, very easily. Rubber molecules do not. They're very low viscosity compared to air molecules. So anywhere that the rubber molecule goes into a cavity, it's going to push the air around. And if the rubber can actually capture, if it can trap the air will not be able to permeate out, because rubber is a good seal. So if we can actually get some of the air out, some of the gases out prior to the rubber going in, we have less chances of having an air trap or the defect associated with that. We know about using tires and seals to maintain pressure. We use this all the time. It's easy to understand how that rubber can flow into a cavity. This seems loud to me. So it's easy to see how that rubber can flow into a cavity and end up trapping air somewhere in the mold and preventing that air from being able to escape. That's the reason we want to get some of the air out. So air removal from rubber molds during the molding process is necessary to achieve good molded article. So air removal often includes removing outgassing of volatiles from the uncured rubber. It's not just air that is actually inside the mold. There can be adhesives that you're using for rubber to metal bonding, and that will gas out and put other gas type stuff. Sometimes what we need to be looking at, what a vacuum is doing, is not just removing air, it's removing gases. And air is a gas. It's just one of the gases. The volatiles that are inside the rubber part itself can actually also have outgassing that takes place. So there's a lot of gas-like molecules that show up inside the cavity. Some of it is air, some of it's not. So in consideration of the idea that two bodies cannot occupy the same space at the same time, rubber molecules cannot occupy the same space that an air molecule occupies. Imagine that you're driving down the road and you're in your car, and there's someone driving down the road next to you in their car. And for whatever reason, you both decide to occupy the same space. You can't do that. We call that an accident, because the two cars cannot occupy the same space. Well, that's kind of what happens with a rubber molecule and an air molecule. They can't occupy the same space. And the rubber molecule is like a bully. It's going to actually push the air out of the way, and the air is not able to withstand that. So therefore, the air molecules must vacate their space in order for the rubber molecules to claim the mold cavity. To remove or vent air faster to avoid overheating the air is what's called desealing. This is something that people really struggle with and don't even know it happens. When we turn on an air compressor, we're compressing the volume of air from a large space to a small space. And it's called compressing air. We have a device that's called an air compressor. When we do that, a lot of heat is generated. To compress air generates heat. To let the air escape is for it to cool down. So if rubber gets into a mold cavity, traps some air molecules, pushes on them, the rubber will actually begin to compress the air into a smaller volume, which will actually heat up the air. It can heat up the air so fast that the air, now hot, will cure the face of the rubber that's pressing against the air. And it won't go any farther. And we call that dieseling, kind of like a diesel engine. That's the way it works. So to minimize the potential premature curing of the leading edge of rubber, we want to get rid of some of that air so that we don't have the blisters, so we don't have porosity, so that we don't have knit lines. Now, removing air from a cavity is the introduction of rubber between, depends on what units you use, 25 inches of mercury, 635 inches of mercury. Basically what that means is that you're using somewhere between 75 and 90% of a full vacuum. Most people consider that outer space is a perfect vacuum. Close enough. We don't want that kind of vacuum. You actually can't get that kind of vacuum in your mold. And so if we're using somewhere between 25 and 10% of all of the air out, it means that still has some air in the cavity. All of the air is not out. It's now spread out. If we were to take all of you as air molecules in this room, air molecules slip past each other, we would evenly disperse. We would actually we wouldn't be clumped up in one corner. We would be spread evenly across the room. If I took out 75% of you, so there's only 6 or 7 left, now those air molecules would still spread out. There'd just be one here and one there. They'd be spread very far apart, which makes it easier for the rubber to go in and push the air out because there are less air molecules. But there are still some air molecules into the cavity. The methods that are used for compression molding generally involve techniques in which the actual mold is put into a box. We have a lot of presses here in this display in the exhibition that have a vacuum box. And so the mold is actually up inside the box like an oven, and the vacuum is pulled on the box and everything that's in the box, and so that's how the air gets out. The vacuum press is adapted to operate and apply vacuum functions during the molding cycles, and molds are placed in the press. When you're doing transfer molding, usually it's the same way. You end up putting the transfer mold into the vacuum box because it's a little more difficult to actually put a function into the mold itself. For injection, most of the time we don't put an injection mold in a box. We actually put seals between the plates and we pull vacuum in the mold. So the vacuum is in the mold rather than the mold in the vacuum. Injection presses are adapted to operate and apply a vacuum function accordingly. You'll see those examples here. There are several different molds here in injection presses that have a seal ring around them. Now, some of the advantages of vacuum, obviously, it removes some of the air and gases out of the mold cavity, which minimizes the restrictions that would have otherwise impeded the ability for rubber to properly fill the area. It reduces undesirable effects and impact of mold fouling. Air tends to oxidize, and so some of our mold foul, the dirtying of our mold, is accelerated by having air in the cavity. If you can pull a vacuum, your mold won't get as dirty as fast in many of the compounds that we're using. Some more advantages is to minimize the likelihood of knit lines. Well, those knit lines are where flow fronts come together. If there was any air that was preventing the knit lines, the flow fronts from coming together, then that would be one of those reasons that by getting air out, there was less chances of a knit line. It can improve the surface finish of a molded article. It can reduce scrap products due to air traps and a lot of other defects that can be raising your cost of quality. Here's a progression of logical advantages of vacuum. Using a vacuum can reduce your cycle times. Here's why. Improved surface finishes tend to imply that you have less dirty mold surfaces. Okay? If I have a less dirty mold, it tends to imply I have less mold foul. If I do have less mold foul, that tends to imply that I need to spend less time wiping my cavity every time between heats. If I do spend less time, then the next cycle starts just a little bit sooner than it would have otherwise because I didn't have to spend as much time cleaning the mold. If I do start the cycle sooner, that tends to imply that I lost less heat during the service time. If I did lose less heat during the service time of the mold being open, then I don't have to recover as much lost heat. This may only be a little bit, but this is all the logical progression that takes place. If I have less heat that's lost, then in order to keep going, either I need to take my temperature settings and lower them in order to maintain the same molding cycle, or I need to shorten my molding cycle to maintain the same temperatures. There's a not so obvious advantage of in-mold vacuum. Now this would be like for an injection mold. With an injection mold, rubber is not in the cavity. With a transfer mold, rubber is in the transfer pot. With a compression mold, rubber preform is in the cavity during the time that the vacuum is being pulled and established. With an injection mold, there's no rubber in the cavity. The rubber is up in the injection unit, not in the cavity. And so while the rubber is in a compression cavity or in a transfer pot and plunger, during the time that the vacuum is being pulled, the rubber is exposed to some heat. It's on the hot surface. It may not be on there very long, but it's on that surface. You have to wait for a few moments for the vacuum to be established. In an injection press, you don't have that problem. You still have to wait for the vacuum to be established, but rubber's not sitting on a hot surface. And so that's a not so obvious advantage of using in vacuum in injection. Here's just a typical old press that's got 4 posts on it. This does not have any kind of vacuum system in it. I could modify it and put some vacuum in it. I could modify a mold and make some vacuum that's in the mold. But here's sort of the same kind of press, except it's got a vacuum box. And you'll see a lot of vacuum boxes similar to this around in this display. The entire mold goes up inside the box. Here's a typical one. I'm not even sure what kind of presses these are, but these are kind of the things you'll see around here. There's a mold that goes up into the box. There's a seal on the bottom of the box that comes down and makes a seal, and a vacuum is pulled inside all of that. The bigger that the mold is, the less air is in the vacuum box. The smaller that your mold is, the more air that there is around the mold in the vacuum box. You still have to take a certain amount of time to pull a vacuum and get established. This is called a slab side press instead of a post press. These are fairly easy to adjust and put a chamber. So instead of a vacuum box, they build chambers out of this. So it's like an oven. You have a sliding door that locks. There's a seal on the face. I show this little sketch also because it shows an accumulator tank. Now, in the vacuum presses that we have around here, there's an accumulator system of some kind. And what that does, it's pulling a vacuum. The pump is pulling a vacuum on a large area of air. And then a 3-way valve is immediately exchanging and opening up this vacuum area to that area that's in the press or in the box. And just literally in a couple of seconds, vacuum is achieved good enough for molding. If you don't have an accumulator tank, then you have to wait for a pump to pull down the vacuum, however long that takes. In a compression mold or a transfer mold, now you've got rubber sitting on the mold even longer while you're trying to pull a vacuum down. Depending on the size of your pump and how efficient it is will determine how long it takes to establish that vacuum. Here's an example of another chamber, a vacuum chamber, not a vacuum box. And the accumulator tanks were all down underneath. Some of the advantages of a vacuum chamber. I haven't seen one here in this show, but a vacuum chamber, the mold does not require preparation, such as vacuum channels. Just any mold will do. No vacuum seals required at the parting lines, and no considerations for how best to completely seal the mold. The vacuum port required is outside the mold, so it's very simple to put any kind of mold into the vacuum chamber. Here's some typical units that we use, and there's a lot more depending on how you do it. Most of the time we're using PSI or inches of mercury. Either way, what we're dealing with is a percent of an actual vacuum, and we never really achieve 100% vacuum. That isn't what we don't even want that. It's been well documented that if I got too much vacuum, I can actually create, on my rubber, I can actually create a vapor pressure reversal that actually allows some volatiles that are in the rubber to leach out and actually jump across a vapor barrier into my vacuum that I didn't want in the first place. And so sometimes less vacuum is actually better. This is kind of where we choose the sweet spot. So somewhere between 75% and 90% of a full vacuum, these are the numbers that we're trying to achieve. And this is usually best. If you start getting less than this amount of vacuum, you may not be pulling enough air out. If you try to get much more than this, you may actually create some problems with your molding defects. And so this is typically where we're trying to achieve, regardless of which unit that you're using. It's important to point out and understand that 75 to 90% effective vacuum means that there's still 10% to 25% of the original air still in the mold cavity. Easier to push around, easier to get out, but it's actually still in there. So some people are surprised when they end up with an air trap, but yet their vacuum is working. Well, that's because there's still some air in there. So we'll sometimes not use an air vent. We won't use a vacuum vent in the mold. It's not as necessary, but it is very helpful if you do put one in there. That remaining 10 or 25% of air molecules will be relatively evenly dispersed throughout the mold cavity void. Therefore, with much less air molecules widely dispersed in the cavity, the rest of the air can get out and less likely to be trapped. So as a result, it's important to understand that the last point to fill in the mold is in fact where the air molecules are likely to be pushed, and that's one of the places that we do in designing that system. Now, in some molds, excessive vacuum is bad, kind of like above 90, above 95%. If you manage to get to 98%, you might actually have some problems with the vapor pressure at that flow front of your rubber. Most vacuum systems are being used this way. We don't really get to this kind of thing. The type of pump that it would take to get anywhere close to a perfect vacuum is not what we normally use in the rubber industry. So a vacuum pump is essentially an air compressor, except in reverse. And so we're pulling air out instead of trying to compress it. There's all kinds of different vacuum pumps. There's rotary vanes, piston pumps, diaphragm pumps, rocking pistons, and then there's linear pumps. And for most of the time, we're actually wanting to use a system that is like this. We can have if I was to have a chamber and a straw, and I was trying to suck all the air out of something, this is as good as I could do right down here. Not a whole lot. We need something that gives us a lot more suction and a lot more volume. And so depending on the type of pump that you have and the amount of volume of vacuum you're trying to suck and remove, that's the reason you choose certain pumps over other pumps. Here's an example of what we could do without an accumulator tank. If you imagined 1 cubic foot, that's just this much space. If I didn't have a very efficient pump, it could take several minutes to actually pull a full vacuum on just a cubic foot. Most of the vacuum boxes are larger than that. They're almost a cubic meter, certainly a cubic half meter, and it would take a lot longer to pull that. So we use the accumulator tank so that we can pull the vacuum in just a few seconds rather than minutes, because with compression molds, and especially with transfer molds, we don't want the rubber sitting on the mold any longer than we have to. With injection molds, it's not the same, not for the rubber, but it's cycle time. So you don't want to extend your cycle time any longer than is necessary. When using a vacuum that's incorporated into a mold, such as an injection press, an accumulator system is often sized to minimize 2 to 4 times greater than the volume of the cavity, meaning that you don't have to have as much air, but you've got to pull some air out with the accumulator system. Preferably, I like 7 to 10 times, and if it was really up to me, I'll even go bigger than that. It depends on if your accumulator is sharing multiple presses. If it's a dedicated press, then you may not have to have quite as much extra space in there. When you're using a vacuum box or a vacuum press, such as with the presses we have around here, an accumulator system is often sized 3 to 5 times greater than the capacity of that volume, so that you have enough room to be able to pull that vacuum out. Preferably, I'd rather have this when it's my design, and that's only because I sometimes can't have a whole bunch more. An accumulator system can be restored to its set point while the molding cycle is going, because you don't have to hold and pull a vacuum the entire time of your cycle. You share the vacuum with just a few seconds, and then you can turn it off in the three-way valve, and a very simple pump, a low-cost, not so efficient pump, can be used to restore the vacuum into the accumulator system while the next cycle is taking place. Once a desired level of vacuum is achieved, the vacuum can usually be turned off for the balance of the molding cycle. Very often in the presses like you have here, after the vacuum has been established, you'll actually see the vacuum box raise up. They'll keep it close, but they're trying to save the seal, the vacuum seal that's on the bottom edge of the box from being in contact with the platen. And so they'll just open it up a little bit, but once the vacuum is accomplished and the mold is filled, there's not a whole lot of need for the vacuum to continue. A level of vacuum can be held during the remainder of the molding cycle using a three-way valve or a check valve. And if a closed valve is involved, then you don't have to use a pump. It's usually undesirable to use a vacuum pump to just keep pulling a vacuum, because now you're going to work your pump, you're going to wear out the seals, you're going to wear out the pump, you're going to increase pumping costs that you get nothing for. It's not any value to you. If holding a vacuum during the entire molding cycle is dependent upon continuous pump draw, then high pumping cost is going to be incurred. And continuous pumping of the vacuum pump increases pump maintenance and will shorten the life of the vacuum. I don't even actually know a reason to do this. Some people do, but I don't know a reason, not a valid one that makes any sense whatsoever. Rubber flow, as it fills a cavity or a runner or any other empty space, requires back pressure in order to force the rubber to actually fill that mold. The principle of requiring back pressure is exploited in mold designs to prevent rubber from actually filling or clogging vacuum channels. Here's what I mean. Let's suppose this was an injection mold. There's a seal around the perimeter here. There would be an O-ring or some kind of dovetail seal between every single plate. And so between all of these plates, each one of these plates, there's going to be a seal like that. And those O-rings will form the vacuum. When this is actually located, vacuum is located only at the parting line of the mold, and the vacuum may not be effective depending on vacuum levels between the mold construction and the plates. Some people have to be very careful when they go to pull a vacuum inside the press. If you actually close up an injection mold too tight when you're pulling a vacuum, you might not actually establish a vacuum in the press or in the mold itself. So we have to make sure that there are vacuum vents, some channels that can actually work with that. So here's another example of a vacuum seal that is around the entire mold area. It's round, and this is the vacuum channel. So these vacuum channels will be inside. There's cavities. This is just 1, 2, 3, 4, 5, 6, 7, 8. There's a whole bunch of cavities in this area, and we're pulling a vacuum that is in here. It goes down through a hole, out underneath the vacuum ring, and out to the pump. Now, if I was in this room and this was a mold cavity in here, and every one of these chairs was something that we were going to mold with, the vacuum pump is over there somewhere. And so there'd be a tube that came through the wall and into this space where the mold cavities are, and it goes out to the vacuum pump. There's a vacuum gauge at the other end of this tube at the pump, and it's supposedly reading a vacuum that's 90% of a full vacuum. Yay, that's good. Now, if in fact somewhere between here and there someone stepped on the hose, kinked it, or something got in the hose and clogged it, guess what the vacuum gauge at the pump would read? It's going to read 90%. Guess how much vacuum I would have in the mold? None. And so using a vacuum gauge at the pump is not a proof of the vacuum that is in the cavity. So I like to do something extra. I like to have a backup that is taking place in my mold. Here's some examples of how that we do a dovetail. There's all kinds of ones. This is actually one of mine. So this is one of my dovetail designs, and the gasket that goes in there. And so you use a dovetail cutter and make a space for the gasket to go all the way around the perimeter. This is courtesy of some of the folks at Desmond. And this is where the back pressure issue comes from. You're looking at a cavity channel down through here, a mold cavity, and this is a tear trim, and that's a little tear trim. But right there is a little channel, a vent channel, that comes off to the side, and it's slightly reduced by a certain amount of distance below the parting line, and then it gets deeper. And then it turns, and there's another little channel and a groove, and finally there's a hole that goes down and out to the vacuum. Now, the ability for rubber to actually flow in there and fill up that hole is almost impossible. Because what the rubber has to do, it has to fill into this cavity, has to fill up the tear trim, and then somehow start going across as molecules, going across this real thin, hot surface, and make its way into here. Now, when the rubber gets into this deeper channel, it stops right there. The only way that it can fill up this deeper channel is for more rubber molecules to keep coming through this little vent and push it. When it finally fills up this entire channel, that's when it develops enough back pressure to try to go down this channel. Until it can fill up this channel, it can't even get into there. Rubber doesn't flow like water. Rubber flows only when the rubber molecules are pushing them to actually get in there. And so this is using back pressure in the design of the vacuum vent in order to be able to do that. Here's the example of these dimensions for this shape is what's shown here. They're very, very small. And so this is shown in inches. I don't think I have this converted. Yeah, there's some millimeters right there. So the vacuum vent is small. We're trying to find a way to keep rubber from being able to flow there, but make sure that air can pass one way or the other, both in vacuum and in venting. Here's another form of it. This could have been one of those insulators like is used on the power lines, silicone or something. Once again, there's a little vent. Here's the tear trim, but there's a little vent that's off of the tear trim going into a much bigger vent, big channel, and then backwards into that hole. And so the idea is to keep the vacuum port, the vacuum hole, from being able to be clogged up and rubber from being able to get there. Here's some experiences that we've had. All vacuum systems are not the same because the molecules are not the same. If I'm going to actually show a vacuum vent, here's what I might be able to do for an FKM vent, like a Viton, a fluoroelastomer. But here's what my vent has to be for an LSR or a LEM material, something that's much more lower viscosity. And so depending on the viscosity of your rubber also affects the design of your vacuum vent. The purpose of a dump groove is to prevent and protect the integrity of the main vacuum port from rubber migrating through the vacuum connection and into the main vacuum port. And so the location of that vacuum port inside of injection mold is fairly critical. You can't just put it anywhere. You've got to put it somewhere that you can actually make it service well. And so here are just some more examples of a perimeter seal with an O-ring that is in it and vacuum channels that are in there. Here's another one. They're on every plate. You can't just put it on one plate. You've got to put it on all the plates if the seal is in there. Usually the O-ring material is silicone, a good quality, high temperature resistant silicone. There's other materials you can use, but silicone is one of the best materials. I like to put this backup gauge, a secondary gauge. Now, when I was talking about how that I could clog up my vacuum line, I could step on the vacuum hose, I could do something, the vacuum pump would still read a full vacuum, but I wouldn't have it in the mold. So what I want to do is that this line is coming out to the vacuum. I want another independent line that's just going to another vacuum gauge. And so if this vacuum gauge reads the same as that vacuum gauge, then I know that I actually do have a vacuum in the mold. I do this even for my presses, like a tongue U press or a pan stone press, one that's got a box. I'm not afraid to put a separate vacuum gauge right on the box so that I'm actually reading the pressure in the box, not just at the pump. Because I want to know. I want to have absolute assurance that I'm actually achieving the vacuum that I need in the mold. Here's just another view of it. So here's the perimeter seal, talking about that perimeter seal right there. Here's the hole that goes down and out to the vacuum pump. Same thing here. Here's the hole that goes down and out. you'll notice there's a gap. I'm showing a gap in the sketch. It's in the sketch. I actually try to do that. Most of the presses that are made today, you have a choice. You don't have to simply clamp up fully tight. You're actually able to set a small gap and pull the vacuum with the gap and then clamp up. And that usually works a little better to make sure that you actually do have a vacuum that is in there. That secondary independent vacuum gauge location, it can be a quick disconnect. You don't have to have a gauge on every mold. You don't have to take the mold and move it around for cleaning and handling and storage with a vacuum gauge hanging off of it. We can make that very easy to disconnect and keep the gauge from getting damaged. Natural air bleeds can be provided at parting lines. This can help both with air getting out and with vacuum trying to pull air out. And so what I refer to as a natural air bleed has to do with how we grind the plate. And so we can use, if you have two plates that are actually going to made up against each other, I can grind one of them one way and grind another one the other way, and basically those minute micro grinds serve as an air bleed. They serve as a vacuum. They actually can pull a vacuum through there. One of the types of grinds we use are called radial grinds. And these can provide some very interesting blinds. Here's, for instance, a cavity insert. So imagine a round cavity in a mold, however big that it is. That's what this is. The rubber is going to be in here somewhere. And so this is the land that is around the rubber. Instead of having a tear trim, I have this. And these grinds, they're all pointing right to the center of the cavity. So this is a very large magnified view of what those radial grinds look like. Another type of grind is called a tangential grind, meaning tangent. These grinds are not pointed at the center. They're pointed at a tangent angle. These are a little bit harder to apply, but they're actually more effective for the air. The purpose of it is that when rubber is flowing this way and comes up against these grinds, almost like momentum or flow, it will try to come straight across these grinds, and a little bit of film will actually still be on here. But if I have a tangential grind, the rubber's not moving this direction, the rubber is moving that way. And so for the rubber to actually get into the tangential grind, it's got to change directions. And it's harder for it to do that than it is to just shoot straight across. Now these are laser vents, laser etching. So what's in here are the grind vents, and then these are laser vents. And the idea of the laser vents is that they're very, very narrow, but kind of deep. And so here's some dimensions of how those work. You can't machine them in. You have to use a laser to put them in there. They're much more robust. They're kind of more expensive to put in, but they're longer lasting. It's very difficult to tear these up. So microventing is where these laser vents come from. You're actually burning them in. Let's see. And so usually the vent is located opposite of where the gate and the gassing can be. The venting can also be achieved by acid etching, chemical etching, which leaves a textured surface. So there's all kinds of ways that you can apply a non-smooth surface to mating surfaces. It may look smooth, it may feel smooth, but from an air molecule point of view, air can actually still get out. Both of those processes are line of sight processes, which means that you can't use a laser venting or grinding in an undercut. You have to be able to see the surface in order to be working on that. Most of the time, these processes are best if you're using a cavity insert. It's not something you apply to the entire mold. You can use almost any kind of steel, anything that is useful for making molds out of. You can use it for these types of venting processes. Some of the drawbacks to microventing, it's more costly than not, but if it saves a process, then it can be well worth it. Additional care has got to be taken when you're cleaning the mold so that you don't use abrasive cleaning methods such as sandblasting, glass bead blasting, emery cloth cleaning, things like that, because you'll wear away these precision grinds and you'll damage the ability for the air to be able to get out and vacuum. Some of the drawbacks include that large plates may not be suitable for laser, so you use inserts to be able to use that. Here's an example of a mold. This mold is 2 meters by 2 meters. It's a very, very large mold. This is just half of it. The other half is on the other side of this brush and these vortex airs. And you can see all the cavities. They're kind of in a circle, and the other half of the cavities are not visible to us. The laser etching is just on top of these little flanges, and the flanges are raised up above this plate. So when clamping force takes place, clamping force is only on the tops of all of these little cavities, and the laser etching and venting is just on top of those cavities. It's not throughout everywhere else. The clamping force never happens on these surfaces. The reason for the space down between the cavities is because that's where heaters are down underneath. The silicone O-rings are the material and the shape of choice for seals on the face of most of these vacuum seals. O-rings can be continuously molded. That means they can be an extrusion cord that you just cut and splice together, or they can actually be molded. I usually tell people that if you've got a mold that needs a perimeter seal that's this big, then you already have a press big enough to mold your own O-ring. So you can make your own mold for a silicone O-ring that goes into your own press and just make up several of them. There's no need to be buying something from someone else. When you use an O-ring for a vacuum seal, the dovetail shape is usually used to install it. That usually works pretty good. Bias splices of an O-ring seal from a cord stock should be installed with the bias splice oriented so that the splice is under clamping pressure. If you don't know what a bias splice is, let me show you. This is a butt splice. So if I take cord stock and just butt the ends together, a bias splice means it's cut at an angle. And so if I have the two rings and I cut them at an angle, now when the press closes up, it's being mashed together. If I turned it this way, they would be coming apart. So it's called a bias splice. And we orient it so that the splice is clamped during the compression force. Here's one last little thing. It's a process that I invented probably 20-something years ago. It's called chase molds, and for vacuum, I use this process for prototyping and short-run production, but I also use it for vacuum because this is a mold, and these are mold cavities, and so I'd machine a O-ring or a washer or some kind of shape on that and just stick them up in here and make a mold. Well, if I put an O-ring around the top and the bottom one and have a hole coming through the chase, I have a vacuum inside of my little chase mold. I don't have a vacuum press. I don't have a vacuum box. I don't have a vacuum chamber. I don't have an injection mold, but I have vacuum. Here's actually one of my designs. This mold is basically 100 millimeters in diameter for this particular one. Here's one of the ports that goes to my vacuum pump, and the other port goes to my secondary valve so that I can confirm that I actually do have the vacuum that is in there that's supposed to be. So once you're understanding the more about vacuum molding and the principles of it, you can apply it to all kinds of things. If you're using a press that has a vacuum box on it, or you're using an injection press that your molds have a seal into them, the better you understand the principles of why that system is working, the better you'll be able to either troubleshoot it or use it to your advantage in exploiting the principles of vacuum for your rubber molding. And so with that, I think I'm done, and I appreciate your time very much. Thank you.